Okay, thank you very much for the introduction. Today I will be discussing about diverse and adaptive attention convolutional neural network. The outline of my today's talk, I will start with the background, then I will move to a challenge that we are trying to solve in this work. Then I will discuss something about like the problem formulation, then about the proposed approach that we propose for from solving the problem. Then I will present the experimental result and analysis that we have conducted. Then I will finish it with conclusion and future work. So any standard, there is some noise. So any standard convolutional neural network, or in any case like machine learning, follows the following pipeline. The first thing is you collect data, especially if you are working on a custom problem, you gotta collect the data. After you collect the data, the next step is you gotta annotate the data. For instance, if you have publicly available data, which was already been annotated, don't need to do the annotation. But if you collect the data by yourself, you need to annotate the data. After annotating the data, the next step is to build a convolutional neural network model, especially if you are working solving the problem from scratch. You gotta design the CNN model architecture. And when you design the architecture, you take into consideration different factors, such as like intuition, some design principles. By putting those together, you design your network. After designing the model, the next step is to train the model on the training data set and test its accuracy on a validation data. So based on the validation data accuracy, you can tell whether your design is giving you a good performance or not. So based on the validation data set, if it is good, you continue by improving the model. If it is bad, you gotta go back on the drawing board and design again. And that is a very high-level overview of how you approach a computer vision problem when you do it from scratch. So, so my work focused on this stage, which is designing a convolutional neural network model. So in CNN, it has a long story, like computer vision is a very age-old problem. So I will try to cover its evolution since 2010. So from 2010 on, like in 2010 and 11, the most widely used approach was handcraft feature-based approach. In this approach, researchers have to sit down and design a filter or features manually. After they design the features, they use those features to do image classification and object recognition. But that approach wasn't good enough. They weren't able to achieve good performance. But at 2012, ACITTECHLAV was introduced. ACITTECHLAV is a type of convolutional neural network. So with ACITTECHLAV, researchers were able to achieve error rate, were able to reduce the error rate to 16%. So this is a very big jump. And that really showed how convolutional neural network can be successful for such application. Since ACITTECHLAV, researcher has focused their effort on producing and designing a better convolutional architecture. As shown here, in 2012, another architecture came out, which reduced the error to 11%. And in 2014, BGG, which is one of the famous architecture, came out and it reduced the error to 7.7%. So there is also one trend that you can notice here. So when the error is reducing, the number of layers of the component is also increasing. So here it was 8 layers. Now it became here at this point 19 layers. So again, in 2014, Google proposed a Google-Net architecture, which further reduced the error, but it also increased the number of layers again. So in 2015, ResNet was introduced. ResNet is a very famous architecture still to these days. And ResNet significantly reduced the error to up to 3.57%. But when you see the number of layers, it significantly increased, which is 152 layers. So this increase in number of layers brought some consequences. So one of the consequences is an increase in computational cost. So increased computational cost is not bad when you work on server side, but when you work on end user side, such as autonomous vehicle on drones, computational cost is one of a very big problem, because such small devices has a lot of constraints, such as battery constraints and computational resource constraints. So even though the error has been decreasing significantly, but the computational cost of Convolutional architecture has been also increasing. So to closely see this problem, let's pick this ResNet architecture, because it is very famous architecture, and let's take a closer look. So ResNet has a different variation. So as shown here in this table, there are different variations of ResNet in terms of number of layers, as well as the width of the network. So in terms of layers, it starts from ResNet 18, which is ResNet with 18 layers. And ResNet 18 achieved a performance of 29.6 error. And the number of parameters is 11.69. So when you increase the ResNet number of layers to 50 layers, you can reduce the error further to 24.85%. But when you see the number of parameters increase, it got almost doubled from 11 million to 25 million. This is a very big jump. So if you want to improve further the accuracy, you can increase the number of layers to 101 layers and achieve a little bit increase in performance, but with a cost of a big jump from 11 to 44 million parameters, which is almost 4 times. So another approach is to increase the width of the network. So the width means the number of channels at each layer. So for instance, you can double the width, or you can increase it by, let's say, 1.5%. So for instance, if you double it, yes, of course, you can decrease the error, but the number of parameters will also significantly increase. So such approach is not efficient, as I said earlier, for resource constrained devices. And because of such high computational requirement of convolutional neural network, now these days, like especially autonomous vehicles, they gotta carry some huge servers in their trunk to be able to effectively run such complex algorithms. And when you bring these CNN models, especially for drones, they don't have such kind of capability to carry big hardwares. So the only option is to reduce or to follow another approach for increasing the performance of CNN models. So to see how we can reduce such computational cost, let's first see how we can measure the computational cost in the first place. So one of the important functions in Convolutional is the convolutional operation itself. So convolutional operation can be formulated as follows with this equation. So here you have feature inputs, which represent this feature input map. And you have kernel, which are also called filters. So they are used to capture features from the input feature map and map that feature to output feature map. So as shown here, let's say the red kernel starts to convolve over this input feature map and produce output feature, which in this case is this red feature. So this is how convolutional operation works at high level. So using these variables, we can define the metrics that we can use to measure the computational cost. And in this case, we can use floating point operation, which is basically the number of multiplication and addition going on inside the network. And the other is the number of count of parameters inside the network, which is the number of weights and biases inside the network. So these two equations, using these two equations, we can calculate those two metrics. So our objective is to maximize accuracy with less increase in flops and parameters, which can be stated like maximize accuracy, such that while we are minimizing flops and parameters to the minimum level. And the approach that we are using to address this problem is using attention mechanism. So attention mechanism is motivated from human perception system. And attention in human perception system is very crucial for making human visual system extremely efficient. Just to show you how we use attention mechanism, I will show you a picture here. This is a test usually used by psychological experiment. In this test, the experiment is trying to locate this person inside this picture. So let's take like 10 seconds and try to locate this guy in this picture. Okay, so due to limited time that we have, so based on the conducted experiments, psychologists has came to the conclusion that majority of the participants has followed either of these two methods. Maybe you guys also have used the same approach. The first method is feature-based approach, which means you take a feature, a unique feature associated with this guy. In this case, the sweater itself, a horizontal red stripy things. So you try to use this feature as a cue, trying to locate anything that looks like this. For instance, in this case, here you have something like that. So once you get that, you take a closer look. And in another case, you have also the same feature here. So using this approach, trying to locate something is called feature-based approach. Another approach that you might have used is spatial-based approach. In a spatial-based approach, you use a location information. For instance, you might think, okay, this guy most probably be around this area. Maybe he might be dining with these people. So you look around this area, you give more focus around this area and take a closer look at that part of the image. So that is called spatial-based approach. So such kind of attention we use in our day-to-day activities. For instance, even when we are working on our computer, we give most of our attention to the things on the screen. We don't easily get distracted by what's happening around our environment. So such kind of attention mechanism help us to be very extremely efficient. So the concept that we are trying to implement is something similar, but in case of convolutional neural network. So the first challenge that we try to address is in convenient is a feature diversity problem. So by what I mean, feature diversity is for instance, here, this dog has different types of features. For instance, the ears are features, the nose by itself is a feature, the legs, they are features. So the problem is there are different size and resolution variation in features. For instance, we have 3 pictures of dog here. All these are categorized under same class called dog, but the feature size and the resolution is very different. For instance, in this case, we have a bigger feature and a high resolution features. But in these 2 cases, we have smaller features and low resolution features. So this limits and CNN, typical CNN are not designed to capture such kind of variation in image. So that is one of the challenges that we are trying to solve using attention mechanism. And the second challenge is feature importance problem. By what I mean feature importance is CNN capture everything inside the picture. For instance, if you take this second picture, the convenient tries to automatically capture features from the dog, such as like ears, eyes, the legs, the tail, but also it captures features from the background, such as the leaves of the tree, the grass, and something unimportant. But the problem is, convenient, they don't have such explicit power to differentiate between important and unimportant features. So they capture all features equally. So that is also another issue in convenient. So our approach of using attention mechanisms attempts to address these 2 problems. So so this is how we are trying to solve the problem. For feature diversity issue, we try to explicitly capture different types of resolution of features. And for feature ranking problem, we try to adaptively rank the feature importance as shown here. Instead of giving the same value for all features, we give different value for the captured features based on their importance in identifying the given image. So this is the design attention mechanism, how it looks like. It's architectural design. So here you have the input layer. You have the input feature map, and you have here output feature map. So you can assume these 2 as 2 layers in convenient. So you integrate the proposed attention mechanism in between those 2 layers in convenient. So the attention takes input from the previous layer, and it gives output for the next layer. So this is how the design looks when you zoom in each layer inside the attention mechanism. So the attention mechanism has multiple layers. If you zoom in and look closer in one of the layers, you get such kind of architectural design. So this design can be divided into 2 sections. The first section is this part, which is responsible to capture diverse feature. And the next part is the rest of the structure from here and on. And this part is responsible for adaptive selection. So the overall attention mechanism can be presented as follows using this equation, where F represents the attention transformation happening at each layer of the attention mechanism. And if you want to represent it in a more detailed way, you can represent it as follows, where FA stands for the adaptive selection, and FD stands for the diverse feature extraction phase. So the The overall attention transformation can be broken down into the following smaller steps. The diverse feature extraction has two subsections, the dimensionality reduction and the feature extraction phase. And the adaptive selection phase also has three phases, global pooling, learning interchannel relationship, and the final step is the adaptive selection phase. So let's briefly look into these steps. So it starts from the dimensionality reduction. So why we need the dimensionality reduction is because to reduce the computational cost of the attention mechanism itself. If we take the input feature map as it is, the number of floating point operation and the number of parameters would increase significantly. So to avoid that, before we apply our attention transformation, we reduce the dimension of input feature map. So there are two methods that we can use. The first method is the most widely used method, which is dimensionality reduction based on pointwise convolution. The pointwise convolution follows the following three steps. First, you reduce the dimension using a pointwise convolution. Once you reduce from here, as you see, from C out, the number of channels from C out to C reduced, C red, you can then apply your attention transformation on the reduced feature maps. Once you finish your transformation, you have to expand it back to its original dimension, again using a pointwise convolution. So that is what's happening on the third process. So this is good to reduce the dimension. It does the job, but the problem is such dimensionality reduction has shown some side effects because it destroys nonlinear relationship between channels. Like when you apply this pointwise convolution multiple times, it destroys nonlinear relationship among the channels. So for that reason, we did not use this method. Instead, we used a group convolution. So group convolution looks like the following, can be easily represented in this image. So what makes group convolution different from typical convolution is that in typical convolution, as shown here in the first picture, to create a feature map, you have to consider all input feature map into the convolutional operation. So for instance, in this case, to create this one feature map, you have to use all these 12 feature map as inputs. But in group convolution, you can reduce the amount of feature map that you can use as input. For instance, in this case, you can only use 4 of the feature map as input to create one feature map. And for the next feature map, you can use the next 4. So by doing that, you can reduce the computational cost of your model. And such approach is becoming very famous, and it has been also used by one of recent architecture called ShuffleNet. And they used this method and they significantly reduced their computational cost, their architecture computational cost. So in our case, we also used this method, and we were able to reduce the computational cost by a factor of G over C. G stands for the number of channels in each group, and C stands for the number of channels. So after the dimensionality reduction, the next phase is the feature extraction. So for feature extraction, to be able to capture the size and resolution variation in features, we use multiple size filters. The problem was in typical convolution, a common size filter usually used throughout the network. For instance, usually a 3x3 filter. But researchers have shown that different size filters has different tendencies in capturing different resolutions. For instance, this paper have shown that large filters tends to capture high resolution features, and small filters size tends to capture low resolution. So having this in mind, we make this n value variable instead of static. Before it was static, now we make it variable, where n is equal to 2x plus 1. And we limit the x value between 1 and 4. So to show you how it works, like we have inputs, and you pick n, let's say you pick x to be 1. When x is 1, this will be 3, n will be 3. So you use 3 by 3 filter and you do the convolution and you generate a feature map. So the next step, like let's pick x to be 2 and this n will be 5, and you use 5 by 5 and generate a feature map. So just like that, you keep generating a feature map using different filter size. So with this approach, you will increase your chance of capturing different size and resolution variation inside the picture. So one of the problems that we noticed using this approach is how about if the filter size get very big and became like even equal or greater than the size of the input image itself. So for that reason, we limit the filter size not to be greater than 9. So that's why we put the maximum x value to be less than or is equal to 4. If it is equal size as the input, the convolutional concept, we will lose the convolution concept, and it will be a typical fully connected neural network. And we don't want that to happen. If the filter size is greater, that will generate error. So after diverse feature extraction, this is how we finally formulated for the implementation. So after the diverse feature extraction, the next phase is this gray area, which is the adaptive selection phase. So the goal of the adaptive selection is to emphasize the features based on their importance. So the first thing that we do in the adaptive selection is to squeeze this 3-dimensional feature into a vector. So to do that, we use a global average pooling operation, which can be represented using this equation. So we converted this 3D map where each feature will be represented by one vector as shown here. So once we convert to a vector, we use that vector as input information to learn the inter-channel relationship among alpha number of channels. For instance, this is a vector. So we pick alpha number of channels at a time, and we use 1D convolution to learn the relationship among these channels and generate a scoring value based on those that information. So we keep moving this window one step at a time and learn the overall inter-channel relationship. So this is implemented as follows. And when we are doing this, we are learning this W value, this omega, which is the weight that we are learning through the training. And the final output will be this, these scoring values. And we use these scoring values in the next phase to weight the captured features. So in the previous phase, we've seen that we have captured diverse features. Now we have generated a scoring value for this feature. So when we multiply these two together, these scoring values will weight these captured features. So when we multiply them, if the scoring value has a high value, it will emphasize that feature. If the scoring value has a low value, that feature or the corresponding feature will be suppressed. So the intuition behind this is to emphasize important features and to suppress less important features. So this is the overall process of a D2-Net attention mechanism. So once we finish it, we put it into a module-like structure, and we integrate that module, which we call it D2-Net, inside any CNN architecture. For instance, in this case, this is a ResNet 34-layer architecture. So we integrate the D2-Net into the bottleneck location as shown here at 4 locations. So just to make it general, if you have such kind of CNN architecture, you just put D2-Net in the middle of the convolutional block like this, and D2-Net will do the transformation without any additional effort. And it is very easy to integrate. So for the experiment, we used 3 data sets. The first one is SVHN data set. It contains 531,000 colored images, and it has 10 number of classes. And second one is Cypher 100. It contains 60K colored images, and it has 100 number of classes. And the last one is ImageNet, which contains 1.2 million colored images with 1,000 number of class. The size of these images kind of is greater than these 2 images. This has 256 by 256. These images, they are 32 by 32. So for ablation study, the first thing that we experimented or we studied is the effect of filter size. So we picked ResNet 50 architecture, and we also used Cypher 100 dataset for this experimental analysis. So for the filter size, as we've seen earlier in this equation, we have this n by n variable like here. So we tried to pick, we tried to study the effect of this n value. So you could have different combination of such order. If you put them in increasing order, it could be 3, 5 to 7 filter size, or it could be 5 by 5, 7 by 7, or 9 by 9. So we tried different types of combination and compare their performance. So as shown here, a combination of 3 by 3, 5 by 5, and 7 by 7 has given the best performance among the rest. And for that reason, we picked this combination as our design factor. And the other experiment that we conducted is to check how D2-Net is different from a typical convolutional layer. So for that reason, instead of using a D2-Net here, our attention mechanism, we use a convolutional block from the original architecture, which means, for instance, instead of D2-Net, we replicate this block and we use it in the place of D2-Net. So that is what this baseline class shows. So we naively stack a convolutional block. So by doing that, there is 2 disadvantages. The first, the computational cost is way better than compared to, it's much better than compared to the D2-Net, and as well the accuracy is also less than the attention mechanism. So this shows that naively stacking convolutional block will not result in performance improvement. The other experiment is a dimensionality reduction method. So earlier I mentioned 2 types of dimensionality reduction, point-wise as well as group-wise convolution. So as shown here, the group-wise convolution, which is represented from this point to this point, has given a better performance, but the point-wise, which is the last layer, has given poor performance compared to the group-wise. And after that, we check different grouping ratio, which can be controlled with this G value. So out of all experimented grouping ratio, G is equal to 1, or in other words, when capital G is equal to the number of channels, that combination gives the best performance improvement. After that, we move on to the adaptive selection phase, which is the channel attention. And we experimented the effect of the alpha So alpha decide the number of neighboring channels that we consider when we learn inter-channel relationship. So alpha ranges in 2y plus 1, where y is in between 1 and 7. So we limit 7 because of this experimental analysis. So we start from 3, which is from 3 feature maps, and we keep increasing it. And when we increase, the accuracy was also increasing until this point. From this point on, the accuracy starts to keep dropping significantly. So this means the adaptive selection gave the maximum information when it considered at max 9 number of channels at a time. So for that, we picked alpha to be 9. So having that design parameters, we put together everything and we integrate the final D2-Net module with different baseline convolutional neural network architecture. So as shown here in this picture, D2-Net has improved the performance after being integrated with multiple architecture as shown here. So just to clearly show you the difference, we can focus on these 2 lines. So here you have ResNet 50. ResNet 50 means ResNet architecture with 50 layers. And you also have here ResNet 101. This is ResNet architecture with 101 layers. So when you increase ResNet layer from 50 to 101, you can achieve search performance improvement, which is up to 3 point plus percent performance improvement. But the cost is significant. It increased from 23.7 million parameters to 42.69 million parameters. But instead of following that path, you can easily integrate the proposed approach, which is D2-Net, on top of the ResNet architecture, and you can achieve a comparable or even a better performance with negligible cost. So when you see the difference between the number of parameters here, it is almost 0.36, which is way less than what you would have cost if you use the other approach, which is by increasing the number of layers. So this clearly shows that the benefit of using attention mechanism to boost convolutional neural network performance. So the same thing applies for the rest of the architectures as well here, for wide ResNet as well as for the ResNet XT as well. So next, we move and compare our attention mechanism with other state-of-the-art attention mechanism in literature. So these are the best architecture attention mechanism so far, which are squeeze and excitation, bottleneck attention module, convolutional bottleneck attention module. So we did the comparison on multiple different architectures and on multiple data sets. So this one is compared based on Sci500 data sets. So as shown here on each block, our proposed approach has achieved a comparable or even sometimes better accuracy compared to the baseline architecture, as well as compared to other attention mechanisms. And here on SCVHN dataset as well, it achieved a better or a comparable performance improvement. So the other comparison is done on ImageNet 1K dataset. And on that, it achieved a significant increase compared to the baseline. And it also achieved comparably better performance improvement compared to other attention mechanisms. So these numbers at the top of each column represents the number of parameters. So as shown here, the number of parameters compared to the baseline and the D2-Net is very negligible. It's very small, and the performance improvement is very good compared to the increased number of parameters. So after we did the experimental analysis, we tried to go deeper and try to examine what's happening inside D2-Net. So for that reason, we took samples from different part of the network where we integrated the D2-Net attention mechanism. So in this case, as you see in the picture, these two samples have been taken from this part of the network where we integrated this D2-Net module in the network. And the middle one has taken from this part, and the last one has taken from the end of the network. So as shown here, at this stage, D2-Net is not giving that much discriminative ranking values for the feature map. It is almost giving equal values for the feature map. But when we move deeper inside the network, then it starts to discriminate between the feature maps, which means it is kind of giving more values for the feature maps that it thinks are more beneficial to identify the given image and suppressing other unimportant feature maps. And when you get to the end of the network, which is a very important point, the D2-Net attention mechanism activity get more stronger. So as shown here, D2-Net start to strongly rank the feature maps, and it gives high feature map value, high emphasizing value for features that are most probably informative to give a correct prediction, and suppress other features that are not much important for discriminating or classifying the given image. So even when you count the number of features that get high ranking values, it is small compared to the number of features that are suppressed. And this is theoretically expected outcome, because in theory, in convolutional neural network, the earlier layers, which are this part of the network, are more responsible to capture low-level features, such as like edges, circles, like any features that can be shared by any type of classes. But when you go deeper inside the network start to be picky, which means the features that found at the depth of the network are more class-specific features. So by the end of the network will have like decided which features to use or which features not to use. So that is what we see here at this D2-Net adaptive selection activity. So this clearly shows how D2-Net is managing to improve the performance that we have seen in the earlier slides. So in conclusion, the current trend of increasing convolutional performance often results an increase in computational cost. And for that reason, we developed an attention mechanism, which is called D2-Net. And we also experimentally verified D2-Net can efficiently enhance convolutional performance. And for future work, we will develop a loss-based attention mechanism. We are currently experimenting with that by defining a separate loss function for the attention mechanism. And we are also aiming to use a gradient information, which is a back propagation information as input for the attention mechanism itself. And on top of that, we're also planning to apply attention mechanism for object detection and recognition task. So that is what I have for today. Thank you for giving me your attention.
Thank you very much, Abenezer. Okay, is there any question from cyberspace? Any question from cyberspace?
Yes, I have one.
Okay.
Thank you, Abenezer. It's really good presentation, and My question is, I just wanted more clarification if I understood it correctly or not. You said that there is a nonlinear relationship, a nonlinear relationship.
Solomon, we lost you.
Okay, how about now?
Yes.
Okay, thank you. So Ebenezer, you said
Yes.
that there is a nonlinear relationship which exists between two layers that the previous architectures are not considering, and for it being not considered resulted in loss of efficiency and also increased operational cost. So now you're working on that in order to consider for that nonlinear relationship in your network so that the computational cost and accuracy are improved.
Not exactly. So the challenge is there is a limitation on Convolutional to capture a variation in feature resolution and feature size variation in the image. So that is one of the things that these attention mechanisms aim to capture. And after that, trying to adaptively select the features based on their importance to classify the given image. Is that clear?
Yeah, but you are like using in between the layers on the existing architecture, isn't it?
Yes, you're right.
Okay, yeah, so for example, if you stay here, yeah, here, like just like this. So when you put the D2-Net in here, it is because there is something that we are losing by not considering non-linear relationship between the layers. Is that right if I said that way?
Not a nonlinear relationship. The gap is lack of ability to explicitly capture variation in terms of feature size and feature resolution from the input image.
Okay, got it.
Yes.
Thank you.
Yeah, thank you.
I have one question. I'm Mohammed Islam. Thank you. First of all, thank you, Abenezer, for a nice presentation. So, Abenezer, as your model is based on the attention mechanism, did you try to compare with other attention mechanism like guided attention mechanism? Because I didn't see any comparison with other attention mechanism that people work on. And another question is that, okay, you want to answer the first one, then I'll go to this next one.
It's okay. You can finish and I can answer.
Okay. Other one, how you calculate the accuracy, as I believe that there are multiple objects in your data set. So did you try to, how you calculate your accuracy based on the ground truth? And did you try to other evaluation process like misread versus FPPI, I mean false positive per image? So this is my question.
Okay. So for the first question, I compared this method with attention mechanism proposed for convolutional neural network architecture. So SCE, which is squeeze and excitation, is I think the most widely known attention mechanism in NA. And after that, BAM and CBAM also have been used for the comparison. So I use these attention mechanisms, which are the widely used methods for comparing my attention mechanism with the literature. For the second question, I only experimented with image classification tasks or data sets, which are Cipher10, SVHN, and ImageNet. So on those problems, you don't deal with multiple objects. Each image represents one single object. So object detection and recognition is not considered at this stage. So I put that as one of the future work here for object detection and recognition task.
Okay, so you did only the classification task, right?
Yes, exactly.
Okay. Okay.
Thank you.
Thank you.
So, Dr. Omaikar, I think you are muted.
Sorry. Well, I'm sorry. Yes. As I mentioned, thank you everyone for paying attention to Abenezer presentation. As Stacy mentioned, this is our last presentation of the spring semester. The next presentation will start on June the 4th. And we will let you know who are the presenters for the summer sessions. But during the summer session, the intent is to ask many of our own students to give the presentation, and myself and Dr. Kerimuddini are going to be reaching out to you guys, and to basically share your research with others in the community. With that, thank you again. As you know, we had a wonderful and very